We've already suggested two different tests to investigate whether or not there is a linear relationship between two random variables. We're going to go back and take a look at correlation as in some hypothesis test associated with that to again explore this notion. First, starting with the population correlation coefficient, that symbol rho, the population correlation coefficient is between 1 and minus 1. And remember that rho equal to 0 would tell us that there's no linear relationship between the two random variables. Right now, if that were the case, then when we came in to calculate the sample correlation coefficient, remember that's capital S xy divided by the square root of sxx multiplied by syy, that if we were to have a population that were exactly had a correlation coefficient of rho equal to 0, but then we went and conducted a test, so we had a random sample, maybe that was n equal to 30 in that random sample, and we went and calculated in that joint collection of data the R value, and it might turn out from that random sample to be about 0.1. We might do that again, conduct another random selection process and calculate the sample correlation coefficient, and maybe this time it's negative 0.2, and maybe then do it a third time, then we get maybe positive 0.3. The point being that just because your population has a 0 coefficient, when you conduct a random sample, you're not going to get necessarily exactly 0, right? Because it's a random sample and it's just a subset of the population. So therefore, we're going to end up with these kinds of questions of, if I see a sample correlation coefficient that's not 0, then how do I know whether or not I really do have no linear relationship between the two random variables? So we developed a test for a linear association in this bivariate normal population, right? The x and y are both normal, and jointly together they're normal. The null hypothesis that we're going to be working with is that the population coefficient is 0. And when that's the case, then our test statistic that we're going to work with is going to be t distributed again, and is going to be equal to r times the square root of n minus 2 divided by the square root of 1 minus r squared. And your textbook gives some hint as to where that's coming from. Right, and that's going to have n minus 2 degrees of freedom associated with that. So let's take a quick look at our aquifer data and what this would suggest to us. That our R squared value was about 0.838 and our R value was 0.916 rounded, and that makes our calculated t statistic value to be 0.916 times square root of 15 for 17 minus 2, and then square root, oops, no, I did that right, 0.916, that's the R value, and the R squared value is 1 minus 0.838. Don't square it again, right? And that statistic is going to be about 8.81. And if we're doing a significance level of 5%, as we've been doing for many of our examples here, two-sided, then our critical t value is, well, wouldn't you know, it's the same as what it's been every single time, 2.131. And so t naught is greater than our critical value of t, and so therefore we reject our null hypothesis and accept that rho is not equal to 0. That'd be the alternative hypothesis here, and I didn't write that down, so real quick. That's where the two-sided business came from. And of course that's very consistent with all the other tests that we've been doing. Right now, if instead you wanted to test a different kind of hypothesis, that it wasn't equal to 0, but and you already felt very comfortable with that. Instead, you wanted the null hypothesis to be something along the lines that rho was equal to something other than 0. Then, well, it gets messy. All right, so indeed it's quite messy here. If n is large, say greater than 25, then we can use an approximation and get to some sort of a normal type of situation. We start looking at z as our statistic is equal to the arc hyperbolic tangent of r, right, which is also equal to 1/2 of the natural log of 1 plus r over 1 minus r. Right, so arc for inverse and then the hyperbolic tangent function. Right, and that's going, this z is approximately normal with a mean equal to 1/2 of the natural log of 1 plus rho over 1 minus rho, and a variance that's equal to 1 over n minus 3. Right, and our test statistic that you're going to work with then is, you'll calculate z naught based off your sample of the arc hyperbolic tan of r minus the arc hyperbolic tan of rho naught, the value that we're testing, right, times n minus 3 raised to the 1/2 of the power, the square root of n minus 3, right, and then interpret that in the same kinds of ways. If you want to develop confidence intervals associated with this correlation coefficient, it is a similar type of situation. Where you're going to end up with then that rho will be between the arc hyperbolic tangent of r plus z alpha over 2 over square root of n minus 3, and then the lower bound will be, oops, this is all an argument to the hyperbolic tangent. It will be arc hyperbolic tangent of r minus z alpha over 2 over square root of n minus 3. Right? That's ugly. Ugly, ugly, ugly. And you'll see this written out in your textbook in grand detail with an example. Remember that the hyperbolic tangent of an argument u is equal to e to the u minus e to the minus u all over e to the u plus e to the minus u. Right? And of course these kinds of numbers, all this stuff is best handled by a computer than it is trying to work it all out by hand. There's no doubt.